Good morning. We are very pleased to have Professor Christophe Royon here. He just told me that he has been in Rio for Brazil more than 15 times.
I think so. I didn't count, but
so this is more than enough to be considered Brazilian. He did his master in École Normale Supérieure in Paris in 1991. In 1994, he got his PhD from the University of Orsay, Paris 11, and he then was hired as a scientist at the CAA Saclay. He remained there until 2016, and then he moved to the University of Kansas, United States. So he has participated in very many important experiments. The Tevatron in the United States, the HER in Germany, the Atlas experiment. He took part in the boson, Higgs boson discovery that got, everybody knows that got the Nobel Prize in 2013. Okay. And he was awarded with some important prizes, particularly the Nobel Research Award in Germany in 2018. That was a very nice award. And the gold medal of the Mexican Physics Society last year, 2022. Okay. I have two bios here, so sorry for my little confusion. But more recently also, he was a leadership person in the discovery of the Oderon, a new particle, Royon. Don't say right. And also he's engaged in the design of a particle telescope to be launched. I think it hasn't been launched yet. It's working. Okay. So please take the word.
Thank you. So thank you very much. And it's a pleasure to be here again. As it was mentioned, I don't know how many times I've been in Brazil. If it's 15 or 20, I didn't count. But it's a pleasure to see many friends also in the audience. So it's a pleasure to be here. So what I want to discuss today is basically the physics we can do by measuring intact photon at the LHC. So I will define a bit what I mean by measuring intact photons. But it will go from the Oderon discovery, and there are many specialists of the Oderon and soft physics in the audience, actually. So I hope people will be quite interested. And then how we can do beyond standard model physics, for instance, the surf fraction-like particles, using also the same kind of events, so measuring the intact photon in the final state. So I will start by introducing what is elastic scattering and introduction of the Oderon, because especially the young people, maybe this is the first time you heard about this name, Oderon, so it may be a bit weird and you don't know what it means, so I will introduce it briefly what it is. Then I will mention the Tevatron data, so proton-antiphoton data and the TP data from the LHC, how we discovered the Oderon, and then we will move, as I said, to beyond standard model physics. And we will finish also by discussing the detectors that we are working on in Kansas, which are the fast silicon detectors, because we have two applications that we are doing about cosmic rays with NASA, and also which is starting now about the measuring doses for cancer treatment, so in association with the hospital. So we'll finish by describing a bit this kind of detectors. So let me introduce very briefly what is elastic scattering, especially for the young people in the audience. So I guess all of you already play pool. I mean, so what you do when you play pool, you launch a ball against another one. So definitely the people who did this sketch do not know that you don't need to, you cannot hit the black ball, but it does not matter anyway. But the important point is that when you hit two balls together, this is an elastic scattering. It means that usually the balls remain intact after the interaction. You don't destroy the balls after you play. So it's exactly what we are doing in high energy physics. For instance, when you have proton-photon interaction, you have two protons after the interaction, after the collision, nothing else, or the same when you have proton-antiproton collisions. So in that case, like when you play pool, the proton-antiproton, they remain intact. but they are scattered at small angles, exactly from these kind of balls, and they can lose or gain some moment. So this is what we are looking at when we study elastic scattering at the LHC or at the Bremont. So now let's discuss a bit how we can explain this kind of events and how we can measure them. So as I said, so this is what we call a kind of Feynman diagram. So it's always time is going from left to right. So these are the incoming protons, for instance, they interact, we see the double bar, and then the two protons are scattered at small angles. So when I scatter at small angles, so this is a diagram which is rapidity, which is related to the scattering angle theta. This is in fact going very, very far now. So it means that they are scattered at very, very small angles. So if you want to measure this kind of scattering, you see that there is nothing outside the two protons. So you need to measure the two protons that are scattered in the final state if you want to measure these events, because you don't produce anything outside the two protons. So the idea to measure elastic scattering would be to measure these two protons in the final state. And then we'll see it a bit more in the next slide. Let's try to explain how we can see that the protons are intact in the final state. So this will be in the next slide. We try to mention how we can explain this kind of events. So this is the kind of first event you may think of. I mean, there's two kinds of events. Let's start with the right. You have again proton that interact. The protons are supposed to be intact in the final state, and they exchange some gluons between the two protons. And there is a color exchange between the two protons in this case, if there is a single gluon exchange. And there is a property from quantum chromodynamics that especially the young people may have seen during the lecture, that the gluon has the property to radiate many, many ions at each point. So clearly, this kind of event cannot explain elastic interaction because in most cases, the proton will be destroyed and you will produce lots of particles. So definitely, there will be many particles in addition to the proton. So forget about it. It means that the events in which we are interested, where the two protons are produced and there is nothing else, cannot be due with one single gluon exchange. So now let's think about this diagram which is on the left. And you see there is this kind of string which is here. They can produce something in the middle or nothing. And as we see these strings, it must be at least two gluons. It can be two gluons, three gluons, four gluons, five gluons, but definitely not one single gluon. Because again, one single gluon, the most of the time, the protons would be destroyed in the final state. So if we want to explain elastic scattering, we need at least two gluons to be exchanged. So it can be a whole or an even number of gluons, but the minimum is two. Okay. So let's see now what are the tools that we have to measure either proton-proton or proton-antiproton interaction. And I will explain a bit later why we need those. For now, it may be a bit obscure, why do we need PP bar and PP interaction, but we will see a bit later. So for PP bar interaction, you may have heard that there was the machine, which was the highest energetic machine before the Large Hadron Collider and so on, which was the Tevatron, which was located close to Chicago. So it was a proton-antiproton collider with two main experiments, CDF and D0. So we were members also with the Brazil people, we are member of the D0 collaboration, and still member of D0. It stopped running about 10 years ago, now I think, for the last data of the Tevatron, but we still have data to be analyzed. Then for PP interaction, all of you heard about the Large Hadron Collider, I guess, which is located at the border between France and Switzerland. So there are four main experiments that are shown here. So ALICE, CMS, ATLAS, and LHCb. And the results I will comment are also coming from the Totem collaboration. As you will see, they are close to the CMS collaboration, CMS. And so the circumference is about 27 kilometers for the accelerator, and it's located underground between 50 and 100 meters. So now which tools to build? As we mentioned a few slides ago, if we want to measure elastic interaction, we need to detect and measure the intact protons in the final state. And for this, we have some tools that are called the Roman plots. So it's a schematic which is here. why Roman pots? Because Roman, the first one were used, probably in the 70s by the Rome group. So they were invented by the Rome group. That's why we call it Roman. And pots because they look like pots. And the idea is very simple. So you have the beam, which is here, you see in the middle of that cylinder. And what you want is, again, to measure the protons that are scattered at very small angles. You have to imagine that, for instance, CMS is located far away. The protons are scattered at very small angles, and then you want to measure them inside the detector. So when the beam is not stable, let's say there is lots of background, you want to move the detectors far away from the beam, and then the beam is stable, you want to move the detector as close as possible to the beam to measure, again, protons at very small scattering angle. And when I am talking at very close to the beam, we go up to 3 sigma from the beam. So this is really extremely close to the beam. So when the beam, again, for elastic. So this is the tools that we are using to measure the impact photon in the final state. So how does it look like in reality? So we have 2 photos that are here. So this is a view of the Roman pot detector. The beam line is here. And the detector is on the upper part. And this is what we call the bellow that allows to move the detector very close to the beam when the beam is stable. So basically the proton, the scattered proton, they go directly into the detector. And this is here a view in the tunnel where you have 2 green boxes, and you might guess the 2 Roman pots that are located here. So of course it's a very busy environment. There are lots of cables to read out the detectors. So you see there are many, many cables. So this is the view in the LHC tunnel. So now let me introduce a bit, the other one. As I said, many of you, probably the first time that you heard that word. So what is the other? As we mentioned before, what we need in order the proton to be intact in the final state, we need 2, 3, 4, 5, 6 gluons to be exchanged and so on, but not a single glue, because if not, the proton will be destroyed in the final state. So we introduce, from the quantum mechanics point of view, the charge parity, the charge conjugation that changes the sign of all quantum charges. And we introduce Pomeron and Oderon, which correspond to different C parity, charge parity. Pomeron corresponds to positive parity, and the Oderon to negative C parity. So we could say that the Pomeron is made of an even number of gluons, so it can be 2, it can be 4, it can be 6, 8, and so on and so forth, which gives a +1 parity. Whereas the Oderon is made of an odd number of gluons, that's why we call it Oderon. So it means it can be 3, 5, 7, and so forth, which leads to -1 parity. And this leads to the following formula, a simple formula, which are the scattering amplitude. So for proton-proton interaction, this is the sum of the even part and the odd part of the amplitude. And for pp bar interaction, this is the difference between the even and the odd. So already from these 2 very simple equations, you see that with frequencies of differences between pp and pp bar, we might be able to isolate the odd contribution, which will be the Oderon contribution. So this was the idea that we had to look for the differences between proton-proton and proton-antiproton interaction. So this is the general basic idea why they want again to look at potential differences between PP and PP bar interaction.
So what was the Pomeron already found?
The Pomeron is basically was found very long time ago, like in the 50s. So, but what was never found, put in evidence is this odd part of the cross-section, because most of the cross-section is due to Pomeron action. The Oderon part is much smaller. So now let's discuss a bit what we measure. As I said, we measure the impact photon in the final state inside our Roman pot detector. And as usual in particle physics, you count the number of events as a function of a given variable, which is here T. So T is the quadri-momentum transfer square at the proton vertex. And this can be measured by tracking the proton inside the magnets of the LHC of the device. So you can access this value of T, and you can count or measure the cross-section as a function of T. We have different regions that usually appear, and this was the case for a lower energy experiment. If you have very low T, let's say 10 to minus 4, 10 to minus 3, we have the Coulomb region, which is a QED quantum electrodynamics region. Then we have what we call the nuclear region, going up to T, which is a bit less than 1, let's say. And there is the interference region between the two, what we call Coulomb nuclear interference, which is here in the middle. Then there may or may be not some structure that appear, and then at higher T, we reach the domain of perturbative C. So this is basically what we expect to see when we count the number of events inside our detector as a function of. Okay, very good. So, and then we see the following, as I mentioned briefly, we may or may not see this kind of a structure that appears. So you may wonder, why do we see this kind of structure? And this is an analogy with optics. I mean, all of you did this kind of optics experiments. So you use, for instance, a laser. You have here small hole, which is here, and you study the light pattern, which comes through the hole, which is there. And what you all did in the experiment, you see, of course, some basically maxima and minima of the light density that you can observe from the laser. So this is exactly what we see in high energy physics. This is why we call these events diffractive events. You can get patterns of kind of maxima or minima of intensity, the same way that you see maxima or minima of the light intensity because of the diffraction phenomena. So this is the same kind of phenomena that we see in high energy physics. Okay, so before we go to the LHC integration data, we may wonder why the Royon have not been discovered before. If I was mentioning there are already many 50 bar and 50 scattering studies in the past, why didn't see the Royon? And these are some old results coming from the ISR, so about 53 GeV. And you see the black points, they correspond to PP bar, the interaction, whereas for PP interaction, sorry, whereas the PP bar in black and the little 8 point correspond to PP bar interaction. So you see that we see some difference in the cross section in the region of T, which is 1.2, 1.4 GeV. So you will tell me, but I mean, then the other one was already discovered because we see indeed some difference between PP and PP bar interaction. In fact, the situation is a bit more complicated. When I said, if you remember a few slides ago, we have either this Pomeron or the other one which is there can be additional exchanges. For instance, there can be here meson exchange, meson particle can be exchanged between the two. There can be what we call also region exchange at low energy. So it's much more complicated than purely Royon and Pomeron. So that's why this difference was not interpreted as a signal of the Royon, but rather as an exchange of meson exchange that appeared in addition to the Pomeron and the Royon exchange. So it was not a clean proof of the existence of the Royon. So, and before we show the result, let me show you this plot, which is pre-LHC, which are some predictions by different people. I mean, there were others, of course, of this sigmadity as a function of T that they predicted before any measurement at LHC energy. And you see that the measurements are going all over the place. I mean, if you're at IT, there are orders of magnitude of difference between the predictions. And also you see some of them are quite flat predictions, and some of them they show minima and maxima. So the predictions were basically going all over the place before we took the data. That's why it was interesting to do the measurement to see basically which prediction was. And I should say that almost nobody thought about the Royon, maybe except a few series, so that Martinov and Nicholas. So now the first question is how does the data look like? So before we go into the detail, I just want to show you the sigmadity for two values of the square root of S, so 13 TeV in red and 7 TeV in blue. And what you see, what is striking on these two plots, is that you see we get a very smooth behavior. You do not see this kind of maxima and minima that appear around 2 or 4 GeV. Very smooth dependent. So what does it mean? It means that at high energy, you can forget about the meson or the region exchange that I mentioned before, which appear at low energy. So in that case, the situation is very simple at very high energy. We have Pomeron and Royon exchange, and that's it. So this makes our life much simpler. Because if we see some difference between PP and PP bar interaction, then it will be due to the overlap. So it will be a proof of the existence of the overlap. We can forget about the measurement extent or the battery. So first, let me show you the D0 data. So they are the PP bar cross section. So it was just, in fact, measured at the end of the D0 collaboration with this amount of low density, 31 per nanobar, and you have the sigma dt as a function of t, where the protons are measured inside the Roman pod that were installed by D0. And the black point corresponds to the D0 measurement. Then let me discuss a bit the measurement by totem that happened at the LHC. So first of all, what is the advantage of totem? Is that totem has very forward telescope that are called T1 and T2 that cover this domain in rapidity between 3 and 5, let's say, and 5.3 to 6.5. And why is it important to get this kind of telescope? I told you that for elastic events, we have proton-proton interaction, two protons and nothing else. So you want to be sure that there is no particle production in the very forward region. And that's why to get this very forward detector, it's important to veto on any particle that might be produced in the very forward region. So we use these two detectors to be sure that we have elastic interaction. What is also the second advantage of totem, which is more due to the Large Hadron Collider, is that we can run the Large Hadron Collider, first of all, for many different centers of mass energy. In the following, I will use the data at 2.76, 7, 8, and 13 TeV center of mass. And we will see that it's crucial for the Royon discovery. Also, there are different ways, let's say, to inject the beam inside the machine. What we call, technically, for people who know, the beta star, which describes how the beams are parallel between each other. Why is it interesting? So let's comment, for instance, the two green parts that are here. And they show the domain in T where you can measure the signal. So when beta star is quite large, for instance, 2.5 kilometers, you can reach value of T of 10 to minus 4 up to, let's say, a few 10 to minus 1. And when beta star is smaller, this is the case, for instance, here at 90 meters, you can do some measurements in T between 10 to minus 2, and let's say up to 4 meters. So by combining different data taking, we can cover a very large domain. So this will be also very interesting if you want to measure elastic scattering over a very wide region. So let me just show you the measurement of totem, and it's 3 of them. So they are illustrated for as usual sigma dt. So this is the measurement that has been performed at 8 TeV, in the middle at 2.76 TeV, and on the right at 13 TeV. And 13 TeV, you don't even see the uncertainty. You don't even see really the points because the uncertainty are extremely small. The measurement is very extremely precise. So now let's discuss a bit what will be the strategy to compare between proton-proton and proton-antiproton data sets. So let me just go back for 1 second about the different data. What you see for all the data sets from totem, the cross-section is going down, it reaches a minimum, it increases, and goes down. And you see this kind of behavior for all the. And if you remember the P2 data, which we showed here, you see a decrease of the cross-section, and you reach a kind of plateau, and maybe decreases the error bar large at IF-2. But you don't see this kind of deep and blunt structure. So this was this kind of different characteristic of elastic cross-section for PP and PPR. That was the way that we wanted to compare both kinds of the data. So let me also mention one point that I discussed already here. You remember maybe that the Tevotron data were at 2 TeV, and the measurement at the LHC is at 2.76, 7, 8, and 13 TeV. So we don't have, unfortunately, data at the same square dose. So this is the problem. That's why we need to take the data that we have from totem and extrapolate down to the Tevotron energy. If we want to compare the data, there is no other way because we don't have PP and PP bar data the same dose. I will come back about the reason in one of the next time. So, but let me start the strategy. So as I said, the strategy is basically simple. We want to, since we see that for all PP interaction it decreases, reaches the minimum, increases, reaches the maximum, and decreases, we want to define some characteristic of the shape of the cross-section at all center of mass in motion. So this is very simple idea. What is the characteristic of the behavior? And for this, we identify 8 points that are characteristic of the behavior of the elastic cross-section, elastic PP cross-section. So this was the kind of arbitrary. I mean, we choose 8 points, you could have chosen 6, you could have chosen 10, okay, we choose 6. So what are these 8 points? So there are 2 which are objects, which is the minimum and then the maximum of the cross-section. We call the deep and the down. Then we define deep 2, which is the same value of the cross-section as the deep, but at higher speed. Bump 2, that corresponds to the cross-section, same cross-section as that the bump, but at lower speed. We define 2 points that are in the middle in the cross-section, which we call mid 1 and mid 2. And finally, we define bump plus 5 and bump plus 10 that correspond to the value of the cross-section and t. That is 5 times or 10 times the difference of cross-section between the bump and the loop. That is shown here, 5 times 8 and 10 times 3. So this is the definition of the 8 points that we use to characterize the shape of elastic PP cross-section as it is measured by the 10 at 2.767 and 13 p. So before we go to all these points, we take only 2 of them, which is to measure the bump over deep ratio. And this is compared here. You have for PP interaction as a function of square root of x. You have the low energy data that are here in green. You see the total data that are here in black, 2.76, 7, 8, and 13 TeV. And here this is compared to the PP bar data, which is at 1, because of that there is no bump and bump, the deep and bump for PP bar elastic data. So only by using these 2 points, you see a difference between the extrapolated value of the term, which is the flat behavior which is here, and the measurement of PP bar data. There is a difference of about 3 sigma. So now let's use this full data point that we have. Like I said, we measure all these characteristic points. So as a function of square root of s, so this is the position in t, and here the value of the cross-section as a function of square root of s for all these. I will not go into detail, but you see bump plus 10, bump plus 5, mid 1, you see also the minimum, the deep. The bump is somewhere here, it's here in blue. So what we do is to study the square root of s dependence of the t position of the characteristic point and the cross-section of this characteristic. Why do we do this? Because we want to extrapolate this value down to the tevatron energy, these are the stars which are here, in order to compare with the zero measurement. Why is it like this? As I told you, we have square root of s of 2.76, 7, 8, and 13 for the LHT, whereas the tevatron is at 2 TeV. So that's why we need to extrapolate down to 2 TeV to make a direct comparison. So here there are 2 limits. The first one, you see that it's really crucial to get the 2.76 TeV data, because the range of extrapolation is not that much in this domain. If you didn't have this data, then to extrapolate down to the tevatron energy would be very tricky. So these data are really crucial for this population. And also you may ask, well, why don't you run the LHT at 2 TeV? Then I mean, you would not need this kind of gymnastic extrapolation. You would just compare the data and that's it. Unfortunately, life is not that easy because it's very difficult, first of all, to run the LHT at 2 TeV. And even if we are running at 2 TeV, then given our detector acceptance, we would have no possible measurement in this region of the bump and the dip where we do the comparison of the data. So unfortunately, it's not possible to get an LHT measurement at the same energy and the data. Okay, so we have to live with what we have. So what is the next step? So now, as I said, we have the stars to predict the characteristic point at the same energy as the data. So the last step, if we want to compare with the zero data, is to fit this characteristic point to predict what would be the PP elastic cross-section at 2 TeV coming from extrapolating the total data. So this is what we did. So I don't want to enter into detail. I just want to mention that we use for this to double exponential fit, which is shown here. That allows to compute the value of the cross section in the same bin as the D0 measurement. And this is the plot, which is kind of the non-plot that we obtained. So the D0 points are the blue points, and the extrapolated delta from total are the red triangles with the uncertainty, which is the bound, which is. So only by that, you see that indeed you see some difference between the blue points and the red point, the red measure. So the last step is to quantify the difference by using the chi-square method. And what we obtain is correspond to a significant count of about 3.46, which is to see the overall for the difference between BP and BP variance signature. So in addition to this, there is something a bit more tricky that I mentioned at the beginning. We go it in the detail, but this will be more for specialists. If you remember, I mentioned when we discussed the sigmoidity, here it is, that there is this region at very low T that we call the Coulomb nuclear interference region, where you have both, let's say, the Coulomb part of the cross-section, which is QED, and then the nuclear part of the cross-section. And this is around 10 to minus 3, 10 to minus 4. So the first remark is that the data that we use to do this comparison are completely outside the domain of comparison that we did now, because now it was in this region, so more of T around 1. So this is completely separate the data taking, totally count the data that we use for this very routine measurement. So let me go to the example, which is here. So in this Coulomb and interference region, there is the Coulomb amplitude, and the nuclear amplitude is there. So we can measure a quantity, which we call rho, which is the ratio of the real part of the nuclear amplitude at T equals 0, divided by the imaginary part of the same quantity. So this was, there was a measurement of rho and the total cross-section that was performed using very good data. And let me show you the result here. So these are the value of the total cross-section as a function of square root of S. So these are the different measurements which are here from total, and you see that this total cross-section, they favor what we call the blue kind of parametrization. What is the difference? Maybe a bit small, even for me it's pretty small here, but the blue parametrization corresponds to log S plus a log square S term of the total cross-section. Then you have a log square S term for the purple curve, which is here, and the log S term only for the green part, which is here. And if we compare to the raw measurement, which is here, especially at 13 TeV, you see that this parametrization in red, or in blue, sorry, is disfavored, and in green is much more favored. So there is a kind of tension between these two data sets, because the raw and the total cross-section, they favor different kinds of parameterization. And all these parameterizations, there are about 100 parameterizations in this plot, none of them have another actually in their prediction. If you have another, this tension between the different parameterization does not exist any longer. That's why this was considered as an additional possible evidence of the other one, which is independent of the PP to PP bar difference. And this, if we combine the two kind of value of them, significance, which varies between 5.3 to 5.6 sigma, depending on the group. So this was published in a theorem, and this was basically how we found basically the other one by comparing mainly and carbon. Okay, so now let me switch gear a bit to go to beyond standard model physics, as I mentioned before. So we'll use again intact proton in the final set and see if we can say something for search beyond standard model physics. So you see this small cartoon, so there is the father on the scale, they are observing the standard model. Everything is working nicely, but definitely it doesn't look very normal, I would say. It seems a bit complicated. So that's why we think that there could be some beyond standard model physics that exists, but can we see it at LHC energy or not? This is the question. And can we see it using intact photons? So we use the same detector, the same idea. We want to measure intact photon after collision, but this time, each time we are taking data at the LHC, we want to measure possible intact photon interference. And so this was a joint project, and this was following the fact of a proposal we made both for ATLAS and CMS to detect this intact photon in the final state for all data. And this is now a reality. I mean, this proposal was about 10 years ago, and it became a reality. We accumulated about 115 femtograms of data that were collected, for instance, by Siri. So which kind of physics do we want to? So as we said, I mean, if we want to have a colorless effect, we need at least two gluons, which is produced. So this is this kind of diagram which can be produced. We have to jet in the final state. But maybe the students could have argued when I said that, okay, to have a colorless object, we need two gluons. The student might have told me, okay, but we can have photons. A photon obviously has no color, so you can have this kind of events. Sorry, the P will be out, so where each photon emits a photon, and you produce a system which will be colorless exchange because we have a photon. And we will see that when we discuss beyond solar model physics, this will be more this kind of diagram that I will be interested in. We will see in a minute. So before we go into the detail, when we are running at high luminosity at LHC, for people who are a bit specialists, it's what we call low beta star running, where we can accumulate lots of luminosity at the LHC. So what is the mass acceptance? What I am talking about the mass of the jets or the mass of the system X, which is the mass acceptance is start something like at 450 GeV and go up to 2.5 GeV. So you see that you are sensitive to a mass object that can be produced in the final. That's why it's interesting to look for pure standard model physics, because we can get quite heavy objects, again, even above 2 GeV, that can be produced within this thing. So this is clearly maybe a nice way to look for pure standard model physics. So what is the motivation? So one of the motivations is to look for instance, extra dimension in the universe. So the way that photon couple, they may be sensitive to this kind of extra dimension in the universe. So this would be, of course, a major discovery if we see extra dimension at the LHC. And what we are going to focus, I mean, it can be generalized to many other things, is what we call quartic photon anomalous sampling. So what is it? So you see that there is two photons before the collision are here, after the collision are here, so time is going from left to right as usual. You have a quasi-real photon, which is emitting, the two photons interact and produce two photons in the final state. And for students, I would say this is what we call light by light. Light by light scattering is a pure quantum phenomenon. I mean, in daylight, you would not see the light interfering from the light from the other lamp which is here. So here, it's a purely quantum phenomenon where you have two photons that interact together in order, for instance, to produce two photons, or it could be a pair of double boson, Z plus gamma. Many different things can happen when these two photons come. So this is not something obvious, I would say, from the point of view of physics. So this is what we want to study. And again, there can be additional channel, the variation ZZ, gamma Z, or TT bar, as an example that can be produced in this way, but we will focus more on gamma now. So what is the motivation to look for this quartic gamma minus thing? So this is this kind of event that is here, where you have gamma with a loop of new particles that decays into two photons, or gamma to a resonance that decays also into two photons. So if we consider the left diagram first, you have the coupling, which is proportional to the force power of the charge of the particle in the loop, divided by the force power of the mass, and also proportional to the spin of the particle. And for typical Biot-Savart model theory, you expect the coupling of the order of 10 to minus 13, 10 to minus 13, GeV minus 14, just to give you some order of magnitude. Then if you consider the resonance, which is here, so you have the coupling, which is gamma to X coupling to the power minus 2, the mass of the resonance X to the power minus 2, and also proportional to the spin. And it gives, again, for typical Biot-Savart model theory, a coupling of 10 to minus 13 GeV minus 2. So what remains to be seen, can we be sensitive to the very low values of coupling or not at the larger particle level? And before we go to this, let me discuss something that I promised before. Why do I consider the LHC as a gamma-gamma collider? And I forgot about the blue part that we mentioned at the beginning, saying, okay, we have 2, 3, 4 modes, and so on and so forth. And I am now concentrating on the LHC as a gamma-gamma. And this is illustrated on this plot of that. So this is just a reminder of the diagram. So this is a blue diagram that produces 2 photons. And here you have a gamma-gamma that can produce 2 photons via a loop of particles, a loop of charged particles, of course. So it can be quark, it can be leptons, or it can be double bond. And this is the cross-section, so sorry, it's a bit small to see it from the back, as a function of the mass of the 2 photons that are in the final state. The purple curve corresponds to the left diagram. And here it corresponds to 100 GeV, and here 200 GeV. And the black dash on the dotted line corresponds to the right diagram. As I said, the acceptance of the detector starts something like at 450 GeV, which in the diagram would be outside this plot, would be here. So you see that this purple curve decreases very fast. So it means that if you are in the acceptance of the forward detector and you see 2 photons, it means the photon-induced process. From the cross-section point of view, you can forget about the long interaction. If you can measure 2 photons in CMS plus 2 tag photons, you are at high mass by definition, but because of the acceptance of the forward detector. So it means that this is this diagram. That's why for this high luminosity study, we consider the LHC as a gamma-gamma collider. So I want to do a small parenthesis here to probably control we are working at the LHC, you know, is probably maybe not so much for LHCb because the pilot is much lower for LHCb, but for people who work in Atlas or CMS, one of the nastiest background is the pilot. Why is it like this? I mean, you should not imagine the LHC colliding 1 proton, and then you measure. You collide millions of protons together at the same time. And there are many collisions that happen within the same burst crossing. I mean, now, for instance, we can get up to 50 or 60 collisions per burst crossing. So it's really a lot. So what we get is these 2 configurations that are. You have 2 photons that originate from the same interaction as my 2 protons, but there can be this nasty background where you have 2 photons and my protons are coming from additional interaction that we call pi. And this is where measuring all the particles in the pilot state is crucial. As I told you, we measure the 2 photons, for instance, in CMS, and we measure the 2 photons inside the tank. So we are in a situation like at left. We measure all the particles that are produced in the pilot. Why is it crucial to reduce the background? It's because you can measure the mass of the 2 photons or the angular distribution of the 2 photons and compare it with the mass of the 2 photons or the angular distribution of the 2. And this is what we obtain for signal for the ratio of the mass around 1. The pilot background is here in green, much flatter. And the difference in rapidity between the 2 photons and the 2 photons, peaking around 0 for signal, because again, they are originating from the same event, and the flat distribution for pilot. So this means using these 2 quantities, you can get rid almost of all the background. And this is what leads to the best possible performance that we can. So this is just to remind you how the events look like, so gamma. So these are the results. I will not mention, of course, all the numbers that are here, but I want to mention these numbers are for 300% to bar. And for 300% to bar, we predict the background, which is of the order of 0.1. So basically, completely 0 background for a high luminosity after the matching between the proton information and also, for instance, in this case, the photon information. And this is the way we can get sensitivity, which is up to a few 10 to minus 15, GV minus 4, which is better by 2 orders of magnitude with respect to the standard method at the LHC, where we don't measure the impact photon in the final space. That's why it's very crucial if you want to control the background for this kind of searches that we do. And I should mention, even for all cases, WW, gamma Z, T bar, I will not discuss all of them, but for all of them, you gain 2 or 3 orders of magnitude with respect to the standard method at the LHC. So that's why it was the reason why HANAS and CMS pursued this kind of physics and added this fundamental detector to look for anomalous coupling using this method in standard running at the LHC. So I should mention briefly that it can be reinterpreted also by the search for action line particle, where you have gamma to action decay into photon. And this is the sensitivity plot using 300 inverse to bar. So you see that we get about 2 orders of magnitude with respect to standard method at the LHC for masses around, let's say, TeV, or TeV, TeV. And then we cover even a region at high mass that is not covered without being able to detect the photon in the final state. And I should mention very briefly that it's also complementarity with lead light and heavy ion running that covers also this region in the lower mass for the action line part. So I want to stress that this is not becoming a reality. So in fact, we just submitted the CMS publication with the new limits, so which are written here on this and the rest of them using about 103 inverse amount of data. And what is shown also here are the first limits that we get at very high mass concerning this action line particle. Unfortunately, we didn't get many events. There was only one complex event in the data, but who knows, maybe with the luminosity that we'll get now, because now this project of tagging photon in the final state is approved also to run at high luminosity application. So we'll be pursuing this method included also at high luminosity. So I just want to mention very briefly exclusive production of double boson pair. The same way, gamma physics, where you produce double pair, you look in the correlation plot between the rapidity versus mass between the WW and proton-proton formation. The signal will be sitting here. And it led also to new limits in particle numbers. I want to mention in the future, using the full run data, we will be able to observe the exclusive double pair production. So we will be using for this the purely electronic decays of the W, because the dielectric background is too high. And we predict about 50 events for 300 inverse of data of 2 events of background. So definitely, we should be able to observe the standard model prediction for exclusive double pair production, which would be a good cross-check for the measurement that we are doing using the same technique, measuring 2 Ws inside the CMS detector and tagging it. So, what I would like to finish, as I said, in a few minutes that remain, is discussing a bit briefly the detectors that we have been also developing in Kansas. So, I was a bit fast maybe to introduce why we develop this kind of detector. I was a bit fast when I told you, okay, to get to the background is very easy. You can put measure the mass of the system or the rapidity distribution, and we can get rid of the background. Yeah, it's true. But let's come back, for instance, to the WW cases, where you have the W that decays into lepton plus neutrino. Of course, you cannot measure the total mass inside the CMS detector because of the 2 neutrinos that escape detection. So you will never have a good precision on the total mass that is produced inside the CMS detector. So we have to find another way to get rid of the background. And the other way was to measure the time of flight of the photon with very high precision. And when I am talking about very high precision, it means something like 25, 30 picoseconds. 10 picoseconds, it means 2.1 millimeters. But if you know the time of flight the photon to reach the Royon detector, you know if they originate from the same vertex as for instance of the WW. So you can constrain the scattered photon to originate from the same vertex by measuring their time. So this is some kind of a development that occurs in fact for many experiments at the LHC. I mean, mainly for high luminosity LHC, there will be many equipments, many measurements of time, very precise with time flight. But what we did is also, we see this one maybe, is something a bit different to use this time of flight detector for two applications to measure cosmic ray with NASA and also to measure closest during some flash beams. So I will describe to a box of them very quickly. So what we do, the first of it, that I wanted to introduce because it is important for the different applications. So from the electronics point of view, so you have a small signal originating from the ultra-fast silicon detector or diamond detector. So first we design an amplifier using the standard components. And then what we do is very fast sampling of the signal. So these are basically all these yellow crosses of the signal. And we take about 256 points. For instance, here on the decreasing part of the signal, or it could be on the full part of the signal according to the needs that we have. So by doing this kind of measurements, you can get a very precise timestamp where the signal arrived in the detector. And this is exactly the way how we get this kind of picosecond precise timing measurement by knowing when the particle entered the detector. So the first project that we have, as I said, is what we call the Agile project, which is in collaboration with NASA, for Advanced Energetic Ion Electrode Telescope. And this was a request from NASA because they wanted to get a compact, low power, and low cost instrument to characterize solar energetic and anomalous cosmic ray particles. Because they said they need basically something relatively cheap that can be sent in CubeSat or into space. And also, of course, with low power, we don't have much power inside of space. So what we propose is to use these ultra-fast silicon detector and to use multiple layers of fast silicon detector and to measure the signal in the stopping layer using the fast sampling technique. So basically what we call the bright peak, where the particle stops in the detector. So far what we built is fully built in a prototype with 3 layers of silicon detector, and it should be sent into space basically in the next couple of months. It is now waiting for launch at NASA, so it's basically let me just mention briefly how it works. And for this, you have the signal, basically, which shows the signal of the particle that stopped in a given layer of the silicon detector. So this is coming from a simulation, and this is, for instance, for Colóquio. So what do we want? You have here the time. We want the maximum of the amplitude, or 90% of the maximum of the amplitude, and also to measure the duration of the signal. So, for instance, reaching the threshold of the 20% maximum or something. So this is, again, for a simulated signal of the 40 MeV per nucleon of oxygen. So the idea is simple. We will measure, let's say, the maximum amplitude of the signal and the duration of the signal, again, where the particle stops. And then I will show you in the next slide. This allows to identify the kind of the particle and also, at the same time, to measure the energy. So this is illustrated on this curve, where we see the amplitude versus time. And this is, again, maybe small for you, but these are corresponding to the different ions that can be produced. So you have here the lowest mass that are here, like the Royon helium, going to the highest one, like the gold, the lead, and you see that in most of the phase space, this curve will not overlap. It means that measuring these two quantities, you can access directly to the type of the particle, and also by measuring the amplitude, you know what the energy of the particle is. So by measuring these two quantities, you know which particle was emitted and also which kind of energy. And it allows even to distinguish between helium-3 and helium-4, which is quite important for the sound models in astrophysics. So we did also some calibration using the numerosum source. So you have the red point, the red curve, which is here in the middle, which corresponds to the predictions, and all the blue domain correspond to the different measurements that we did in the lab. And we get, again, a good agreement between our measurement and the simulation that we did. So we are now also doing some deep tests of SWADO. So the second application, which is just starting now that I wanted to mention, is to measure the radiation in cancer field. Because you may know that there is a new method with cancer that was discovered a couple of years ago, actually, which is a very intense beam, so a flash beam on the tumor. And what the medical doctors saw in animals is that only the cells with tumor are affected. So it means it doesn't affect at all the cells that are saved. So that's why people think that it may be the future way to treat cancer. And for this, you need like a millisecond beam, so very short beam, and extremely intense. So you need to be able to check the quality of the beam and to be able to measure the dose that the patient received using this flash beam treatment. And that's why we were contacted by the National Institute of Health in the US to say if we could do something about it. Because the traditional method that use ion chamber in hospitals with an answer time, which is a couple of seconds, actually not good to measure the dose for this kind of flash beam therapy. So we use the same idea to use our ultra-fast silicon detector because they are very fast. I mean, we can get a measurement every 20 or 25 picoseconds. So this is why we thought to use the detector for this flash beam treatment. So the first step, what we did is to use our detector and put them inside the beam. It was not flash beam in the Dublin hospital in Ohio, in St. Luke Hospital. That is. So what did we observe? So this is illustrated on these two plots that are here. So this is the beam. And what we do, you see all these spikes that correspond to the signal in our silicon detector. So since we have a very fast detector, we are able to count the number of electrons, in this case, the protons, that enter our detector. So by counting the number of protons, we can, of course, measure the dose that is given to the patient because directly proportional to the number of protons that enter the body. So this is illustrated on this plot, where you see the correlation between the measurements from the usual ion chamber in red and our silicon detector in black. We see a very good correlation. And the new aspect is here, where using our data points, we were able to reconstruct completely the bunch structure of the beam that is used to treat patients. So this is just to give you an idea. This corresponds typically to 150 picoseconds. So the medical doctor, this was the first time, in fact, they saw the structure of their beam that they are using to treat patients. That's why we think we can use exactly the same idea of using the ultra-fast silicon detector to count the protons of the electrons that enter the patient, and then check the machine quality and measure the dose that is delivered to the patient inside when you do this intense beam therapy. So that's why now we just have a project approved by NIH to do the test and to develop these detectors for this kind of application. So this brings me to the conclusion. So first of all, I spent quite a bit of time to discuss about the Royon discovery, discussing the sort of physics at the LHC and the elastic cross-section measurement. Then we discussed also the anomaliscopic part, so which leads to sensitivity to extra-dimension model, action-like particle anomaliscopy with unprecedented precision. And also I discussed at the end the fast timing for HT and application in medicine and cosmic ray physics. So in medicine, people think it may be the future way to treat the cancer using this flash beam therapy if it is confirmed. So this can be quite important. And I would like to finish by thanking all my students that I have at KU that are waiting. So thank you very much.
You know that the question of the other one is questionable. So you know that our objection to the interpretation of your group because it uses extrapolations that would forward later. You know that if people like Donati and Lancelot analyze all data, we model with Royon, Colóquio, other organizations, and they don't see. Okay, this is the question that you know.
Yeah, okay. I want to comment about it because there are 2 points there. I mean, this I think is not disputed by anybody. So the difference between PP and PP bar, and everybody agrees that there is indeed a difference. Because again, this extrapolation is very small, as you said, and also we use many different kinds of extrapolation. The one is shown here, and they lead to within systematics, like less than 1/3 of the systematics, the spread of the different extrapolations. So I don't think it's a big deal. What was more controversial, this is this part to the difference between sigma dot and rho, which is more discussed, as you know, in the literature than the difference with PP and PP bar. Difference with PP and PP bar, I would say this is really difficult, very extremely difficult to get an agreement between the data. I would say it's impossible. You can never get an agreement between the two players. So there is an agreement on this side, was questioned by more people, is this kind of things. I would say that we are preparing, unfortunately it takes more time than we think, but we are preparing a big paper to detail everything that we did. So there will be PRP, basically long paper.
Okay, now let me put a positive question. LHC was running throttle
Yes.
in the beginning of the year. Did you have detectors in the forward direction, already in the forward direction? And do you expect data on throttle and lapsing?
Yes. So for sure, the Roman part, we took data. I mean, definitely when we developed the university data, there were data and we are being analyzed at 900 GeV. Unfortunately, at 900 GeV, we don't have acceptance in this region. But okay. So, and then we took also data at the highest square root of S at the beginning of the year. We were warning that the machine this year was not perfect. The background is much higher than we had in the previous year, unfortunately. So it will be more tricky to analyze because the machine was not delivering a very clean bill this year. Why? We don't know, but the bill was not as clean as bill. So let's see. Yeah, but we took data.
Thank you for a very interesting talk and very overview. I have two questions. First, there is the important projects, detectors also further from the Atlas, which would give access to the smaller and smaller mass. And then being able to compensate somehow this region with totem and AFP and with timing detector.
Yes. Yeah. So first of all, concerning the 400 centimeter detector, as I said, for now, the acceptance starts something like at 450 GeV. I think we have detectors that were further away, so sensitive to smaller angles. We will be able to go down to 50 GeV, so much bigger acceptance at low mass. So what CMS said, they are in favor of having additional detector for the high luminosity period. If there are some interested groups that are, say, they want to do it. So they would not put money in it, but they would welcome new groups that are coming with money and manpower to build these detectors. So now we are looking if there will be some groups. So, but CMS is in favor of doing it, whereas Atlas, on the other hand, said they would not favor, or Atlas would not support it. But CMS is very supportive. So, and concerning AFP, so AFP, they have also they accumulated lots of density also in the previous one, and they have also one paper on AFP, and they are doing some other analysis. I know they are doing ZZ for ZZ events, so doing similar analysis that we do also in the ETS, in the CMS, and doing similar analysis. But they know that normally they would not be running at high luminosity LHC. Whereas now, running at high luminosity LHC is a tool for CMS. This is for us on our side.
A very quick second question. Can you comment on your measurement of the time of flight's resolution in the detector? What about its radiation patterns?
Sorry, about
the new silicon detector, detectors.
Yeah.
What about their radiation patterns?
yes.
The time resolution.
Yes. So there are three kinds of detector that are used at the LHC. So the first one is the diamond detector that is used by Total now to measure the time of flight. So these are very radiation hard and so on, of course. But the time resolution per layer is not that good, something like 80%. But now we have 6 layers. Diamond detectors, which means we divide by square of 6, so you still get a good resolution from the diamond. Then, so this is for the high luminosity measurement. Then for the lower luminosity measurement, it's not the same Roman plots. We have the ultra silicon detector that are equipped in this tactical Roman plots. And there the resolution per layer is about 25 pixels. So that we have the present resolution. And the detector, they should resist basically the full high luminosity period with the most recent one that we have. And then there is another one which is produced by Atlas, not by TMS, which is this quartz bar, it's called quartic, if you will help. And they have very good intrinsic resolution. The light is so few because the resolution is very great. But the problem that can be brought from one bar to another. So this is the difficulty. And also the space resolution is limited by the size of the quartz bar. So you don't get milliliter space resolution, but rather than centimeter space resolution. So these are the three kinds of measurement that are used. And for us in Kansas, we use more, we focus on the upper silicon detector, not super detector.
The micro analysis, some of these groups are finding that in the very central regions, elastic region for the in cycle representation. Some groups find that in a central region, elastic component is increasing. You know that? Trouble.
Yeah, you can show you mean for this is for total construction or visibility?
Yeah, visibility component to be a visibility. And here B for zero, elastic component is increasing. That's a central region.
Yeah, because it's I would say it's a big question we have now for this Royon part. We have no knowledge of the data, we don't know how it varies as a function of square root of S, what is the percentage of the Royon contribution with respect to normal. So we just have this observation, and from this, to obtain what is the relative Royon amplitude and overall amplitude, maybe from this. That's why it would be very good, I think, also to see it in independent channels, because there can be some reason for the different questions related to Royon. So if we had other way to see this correction would be very interesting, independent observations.
It's a very big question.
Yes.
So when you were explaining about the scattering, you said that if you have only one movement, it can radiate and there's a problem, you can have a lot of light. Right? But what is the other change? Why, when we add more movements, why doesn't it solve the problem? Is additional movements already?
Because what you need to have a photon impact, you need to have a colorless. And the way to have a colorless effect of the PCD, the minimum is like two, the one single dimension. We carry one. That's why we need at the minimum 2 and 3 and 4 minimum, but it cannot be a single one. Or as I said, the way you have to carry the load of the field, but you know that come across, not that this is the object, so we do not do everything. But from the PCD point of view, you have one single one, they will carry color, and then the fire you have taken. So you need at least. Is it okay?
Yes, yeah.
I have maybe more integration.
But what's the thing that makes a significant aspects?
So the way that the dogging inside the there is one inside yeah, yeah, the service and what they wanted to do is to get, of course, the highest signal they want. So it's proportional of the charge of the detector, the velocity, and then the field. So they play on these three parts to get really a good signal. So very high field, small detector, so that basically it's very fast by having a small detector, and also lots of charge. This is the way that they did it. By having a small detector, what the tricky part is to get the propagation out. Because then it could be, so that's why you make lots of programs in the 5 or 10 years on the radiation hardness of the detector. I would say 5 years ago, it's possible to use in space or so. And the combination with the development of the fast sampling electronics. That is fast sampling electronics, they have a resolution of 3 to 4. And it's very extremely good development.
Are there further questions? Then